Hello, everybody. Welcome to the week 6 video for Math 4400. So just a few reminders. Your fifth homework is due Monday, February 20th at 11:59 p.m. And the quiz on this video is due on Tuesday at 8:30 a.m. So the key takeaways for this week were solving linear congruences. So these are like AX is congruent to B mod n. So we saw a few different ways to think about that. First, connecting it back to linear Diophantine equations, connecting it to inverses, mod n, and then also just some tricks you can do to do it a little bit quicker in a lot of cases, and you have a lot of homework on that. We also studied systems of congruences. So that's where we have like x is congruent to one thing mod like 17 and another thing mod 13, and we're trying to find an x that simultaneously satisfies both those congruences. And we discussed the Chinese remainder theorem, which tells you you can do that as long as like you're in the situation like 13 and 17 where they're co-prime, their GCD is 1, and also described how we're able to do that. And then we finished up on Thursday by talking about just the basics of primes, what a prime factorization is, and we stated the fundamental theorem of arithmetic, which says prime factorizations exist and are unique. So in this video, what I want to talk about then is quickly the proof of the fundamental theorem of arithmetic, and we'll see how this stuff we did like using Bezout's identity pops up when we try to actually justify the statement that prime factorizations are unique. And then also, I'd like to discuss sort of an application of congruences to studying integer solutions of equations that sort of motivates the kind of things we're moving towards a little bit. So where we're moving is like we've studied linear congruences. We're going to start studying, like, for example, like instead of looking at ax equals b, like maybe looking at like a quadratic polynomial of x instead of a linear polynomial of x. And I'm asking like, when does that have solutions mod n, and sort of especially for specific values of n. So that's where we're going next week. We'll see like one cool example of how this congruence is going to get used to sort of establish sort of an interesting fact. Okay, but first, the proof of the fundamental theorem of arithmetic. So let me recall the statement, and this is copied from your textbook. So it says that every integer can be factored into prime numbers. In other words, any positive integer can be written as a product of prime numbers. And then moreover, that this factorization is essentially unique. So if you sort of have two different ways of writing it as a product, then you sort of up to reordering the way you write it, you're going to have the same thing. So like 11 times 17 and 17 times 11, like those are basically the same sort of factorizations. They just sort of you wrote 17 and 11 in two different orders. But sort of this is saying like, so you can have like 11 times 17 is equal to 17 times 11. Okay, no problem. But you'll never have like 11 times 17 isn't going to be equal to like 13 times 7. So like those, if the prime factors themselves are different, then they're never going to be equal. So when we write the prime factorizations like this, we're allowed to sort of repeat the same prime number twice. So like when I write it as just a product of primes, then sort of like could have like 2 times 2 times 3. So that would be the factorization of 12. Good. Okay. So that's what the fundamental theorem of arithmetic says. It's not so hard to see that everything can be written as a product of prime numbers. I'll go ahead and write down a proof anyway, just for fun. But the real meat of this, or the real interesting part, is this uniqueness. So that's where we'll spend a little bit more time. But first, let me sort of write down a proof that every integer n greater than 1 can be written as a product of prime numbers. And I'm going to do it by induction. There's different ways you can write this. You could also write it by contradiction. But I want to do it by induction just to exhibit a little bit different type of induction than the kind of arguments we've made so far. We do it by induction on n. So sort of base case. So I'm proving it for all n greater than 1. So my base case should be n equals 2. So, well, 2 is prime. It's only divisible by 2 and 1 because those are the only numbers less than 2 even. It's prime by definition. Its only divisors are 1 in itself. Good. And so if you're prime, then in particular, a product of prime numbers. So a product of one prime number. Good. So then let's do the inductive step. So first, let me sort of say the inductive hypothesis. So previously, so when we were doing inductive hypotheses, we went for sort of from knowing something was true for n to knowing it's true for n plus 1. Here, I'm going to do a little bit different. I'm going to suppose I know it for everything, not just n, but sort of everything at most n. So suppose every number less than sort of, so let me say it this way, every number from 2 up to n can be written as a product of prime numbers. Product of primes. Then we'll show n plus 1 can be written as a product of primes as well. So this is sort of a slightly stronger sort of form of induction, where instead of just using like the previous case to prove the next case, so instead of just using the case n to prove n plus 1, I'm actually going to use that we sort of know it for everything up to n to prove n plus 1. But if you think about it, I mean, it still works. I mean, sort of, so I start out by knowing it for n equals 2, and then I'll sort of, after that, I'll sort of know it for n equals 3, so I'll know it for n equals 2 and 3, and I'll use that to get it for 4, and I'll know it for n equals 2, 3, 4, and I'll use that to get it for 5, so I'll know that for 2, 3, 4, 5, and so on. So this actually works as well. And okay, so how do we do this? How do we sort of show this? Well, so either, so we're going to show this. We're going to show n plus 1 can be written as a product of primes. Well, if n plus 1 is prime, then done. If n plus 1 is prime, then itself is a product of primes. So otherwise, n is equal to sort of a times b for both a, b between 2 and n. Sorry, otherwise sort of n plus 1 is equal to a times b for both a and b. I say it this way, for 2 less than equal to a, and b less than equal to n. So if n plus 1 is not prime, otherwise it sort of has some factorization to sort of 2 factors that are both proper factors, but those proper factors are going to be smaller than n plus 1, so they lie between 2 and n. Good. But then by the inductive hypothesis, A is a product of primes. So I can write like A is P1 times PK, and then B equals Q1 times, so Q2 times all the way up to Q, say, M. So A is a product of primes, and B is a product of primes. So m plus 1, which is A times B, is just P1 through, I multiply the primes P1 through PK for A, and I multiply also the primes Q1 through QK for B. So that's a product of primes too. Okay. And so we're done. So we've shown by induction on n, using this sort of stronger form of induction, that's every number is a product of prime numbers. Okay, good. So going back to the statement, we've shown this statement, sort of every integer n greater than 1 has a prime factorization. Again, sort of the more interesting thing is the second part, that so these prime factorizations are unique. So sort of there's not 2 different ways except for reordering the factors to write n as a product of prime numbers. Okay, so let's see we do that. So that's sort of the uniqueness of prime factorization. And really, when you're doing this, there's sort of a key lemma. So the key thing you need to know is that if P is a prime number and P divides a product of two things, A times B, then in fact, P must divide either A or B. There's no way sort of for it to not divide A and not divide B, but still divide the product. So somehow this is the key property that lets us prove prime factorizations are unique. And this really depends on P being prime. This is not true for composite numbers. So for example, like 6 divides 12, which is 4 times 3, but 6 definitely does not divide 4 and does not divide 3. And in fact, for any composite number, you can always sort of produce this kind of example where it divides A, B, but sort of not A or B. So this is really something special about prime numbers. Okay, and so how do we prove this? Well, let's say, so suppose P divides AB. Well, if P divides A, we are done. I'm just trying to show P divides A or B. So if P divides A, we're done. P divides A and we're good. Good. Otherwise, well, I claim if P doesn't divide A, then the GCD of P and A is going to be equal to 1. Why? Well, if you think about it, like the GCD of P and A, it's going to be a factor of P. So it has to be 1 or P. But if P doesn't divide A, it can't be P. So the only other option left is 1. Okay, so the GCD of P and A is 1. We know sort of by the Bézieux identity, so this thing where we sort of unravel the Euclidean algorithm, we can write then 1 is equal to, let's write it as P times X plus, or let me write it this way, I'm going to sort of massage expressions. Let me write it as X times P plus Y times A. So 1 is a linear combination of P and A, where X and Y are both integers. X and Y are integers. So let's just multiply this by B. So let me multiply this equation, both sides. And on the right, so on the left, we just get B. So B times 1 is B. On the right, we get sort of Bx times P plus, so let me write this, XP times B, plus Y times A times B. Okay, and then I'll sort of write that right-hand side as P times XB plus Y times AB. The point is, if I sort of look at P and I look at AB, well, P is divisible by P. So P is divisible by P and AB is divisible by P. So both these underlined things are divisible by P. So I've assumed that P divides the product A times B. So P definitely divides itself. So sort of each term on the right is divisible by P. But if I add together two things that are divisible by P, then the result is also divisible by P. So that means B is divisible by P. Thus, B is divisible by P. Okay, and so we're done. So either P divided A, in which case we're done. Otherwise, we were able to use the fact that GCD had to be, P and A had to be 1, to sort of do this clever expression, multiply by B, and deduce that B was divisible by, that B had to be divisible by P. So it's sort of this clever trick using this funny way of writing 1 by the Bézieux identity. Good. So that's the proof of the lemma. Now let me sort of explain how this sort of implies the uniqueness of prime factorization. Well, let's just look at and basically the idea is sort of you can use that lemma as you can sort of peel off the factors one at a time and sort of show that like the first prime, like one factorization has to agree with one of the primes in another factorization. Let me sort of just show you how that works. Sort of we have like a product of two prime numbers. So like say I have P1 times P2 is equal to Q1 times Q2 with sort of P1, P2, Q1, Q2, all prime. So in this situation, I wanted to do so like maybe that P1 is either Q1 or Q2, and P2 is either Q1 or Q is sort of the other one. So sort of that these are really the same up to reordering. Good. So if I start with this, well, P1 divides P1 times P2. So that since that's equal to Q1 times Q2, I get that P1 sort of divides Q1 times Q2. So that's where I sort of extract from this. I extract the fact that sort of I write Q1 times Q2 as this product P1 times P2. That tells me that P1 must divide this. But now the lemma tells me that's either P1 divides Q1 or P1 divides Q2. So that's what my lemma says. Since P1 is prime and divides that product, it has to divide one of the two factors. Well, if it divides the first factor, then P1, I claim that P1 is actually equal to Q1. And again, that's because Q1 is also prime. So since Q1 is prime, the only factors are itself and 1. I mean, P1 is a prime number, so it's not 1. So if it divides Q1, if it's a factor of Q1, it has to be equal to Q1. Good, so P1 is equal to Q1. So this was sort of since Q1 prime. But okay, good, so I get P1 is equal to Q1. But then if I sort of plug that into this equation, so I can sort of substitute P1 for Q1 now, I get P1 times P2 is P1 times Q2. So I just divide out by that P1, and I also get that P2 is equal to Q2. So I sort of peeled off that one factor, and then that let me peel off the next factor. Great. And well, okay, so that was if P1 divides Q1. Well, if P1 divides Q2, you argue the same way. You sort of just sort of looks exactly the same. You sort of just exchange Q1 and Q2 everywhere in the argument. And so more generally, like if you sort of have a product of more than one prime that sort of equals a product of more than one primes, you can sort of do the same trick using this lemma to peel off the different factors. Okay, great. So that's the proof of uniqueness in prime factorization. Good. Okay, so moving on. So we're sort of starting next week, we're going to start talking about sort of solving more general congruences. I just wanted to sort of give you an example, though, of like how congruences can sort of help you answer like just like some like basic question about numbers. So here I have a picture of the Mordell curve. This is of a Mordell curve. So this is x cubed plus 7 equals y squared. So I'm looking at sort of all of the points where sort of I have the square of one coordinate is 7 more than the cube of the x coordinate. And then if I sort of draw this out, so here's like a graph sort of one scale, then sort of going to graph at higher and higher scales. And if you look at these graphs and you sort of stare at them, well, it's pretty hard on this one, but on these two, if you stare at them, what you see is actually sort of it just misses sort of all these integer points. So this curve sort of never seems to hit these lattice points that have integer coordinates. And it turns out this is really true. So this is really true that there are no integers x and y such that x cubed plus 7 is equal to y squared. In other words, there's sort of no square that's 7 more than a cube. This is kind of just like a fundamental fact about integers. There's never a square that's 7 more than a cube. Like, so it's very easy to say, but like if you look at this, like you don't know how could you ever justify this? I mean, you could draw this picture and sort of go up to finer and finer scale and sort of bigger and bigger x's and y's, but like how do you know this is really true? Like you never find integer x and y that satisfy this equation. And well, the way we'll be able to do it is sort of using congruences. So I want to go through a proof of this just so I can illustrate sort of how you can do this. So let's suppose you have a solution. And so we'll sort of try and use congruences to show that we can never have integers x cubed plus 7 equals y squared. And we have to sort of break into a few different cases to do this. So the first case is a case of where x is even. So another way to say that is sort of x is equal to 2u for u an integer. So then, well, x cubed plus 7 equals y squared is the same as saying 2u cubed plus 7 equals y squared, or 8u cubed plus 7 is equal to y squared. Okay, and so if I look, if I take that sort of modulo 8, so this would imply, so if I had a solution, that would imply that 7 is congruent to y squared mod 8. So if there is a solution. So if I had some x and y that can make this happen, then if I just looked at sort of this mod 8, well, this says y squared differs by 7 by a multiple of 8. But if I sort of look at the possible squares, mod 8, 7 isn't one of them. So to compute sort of all the possible squares mod 8, I just have to sort of square the numbers 1 through 7 and look at what I get. Mod 8, and well, I'll get 0, sorry, the number 0 through 7. So I get 0 squared, that's 0, 1 squared, that's 1, 2 squared, that's 4. And actually, it turns out that's it. So like if I do like 3 squared, that's 9. So that gets me back to 1. If I do 4 squared, that's 16, which is 0 again, mod 8. And so the only, and so on, and you can work it out. Like 5 squared is 25, that's 1 again, mod 8. So if you look at this, you see that the only possible squares mod 8 are 0, 1, and 4. So 7 is not a square mod 8. So this can't happen. So there's no way we could have a solution where x is even, because that would violate this principle that the only squares mod 8 are 0, 1, 4. Because we had a solution that would tell us that the 7 was a square modulo 8. Okay, so already sort of with very little effort, we've ruled out the possibility of having a solution where x is an even number. With a little more work, we can also rule out x being an odd number. So let's see that. So using a similar argument, if x is odd, then I'll see that x is actually congruent to 1 mod 4. So how? Well, so I have the equation is x cubed plus 7 is congruent to y squared, is equal to y squared. So this implies sort of, if this is true, then x cubed plus 7 is equal to, sorry, x squared, let me say it this way, x cubed plus 3 is congruent to y squared mod 4. So if x cubed plus 7 is equal to y squared as integers, well, definitely they're congruent to each other. I'll just leave this as a 7, sorry. We could change it to a 3 once I go mod 4, but let me just leave it as a 7. Good, so x cubed plus 7 is congruent to y squared mod 4, but x, I mean, sort of a priori, since x is odd, well, either x is 1 or 3 mod 4, but if x is congruent to 3 mod 4, then so then x cubed is 27. So this is 27 plus 7. So if x is 3 mod 4, then sort of x cubed is congruent to 3 cubed mod 4, which is 27. So I get 27 plus 7 is congruent to y squared mod 4. 27 plus 7 is 34. So I get 2 is a square mod 4. But the only square is mod 4. So just like looking at the squares mod 8, so these are 0 and 1. So I can't have x congruent to 3 mod 4. So this sort of gives me a little bit of information about x. I deduced that x is congruent to 1 mod 4. And this was just sort of by analyzing solutions to this equation mod 4. Okay, well, if x is congruent to 1 mod 4, well, then x plus 2 is congruent to 3 mod 4. And I'm going to claim, actually, I can do a little bit better. So I claim I can actually get sort of a prime factor of x plus 2 that is congruent to 3 mod 4. Okay, so the reason is the fact that x plus 2 is congruent to 3 mod 4, that just comes from adding 2 to x congruent to 1 mod 4. Well, it has, but x plus 2, like it has prime factors. There's actually, so I mean, you have to rule out negative numbers, but sort of, you can rule out negative number. Okay, so I'm telling a little white lie, and I need to know x plus 2 is sort of has absolute value greater than 2, greater than or equal to 2 to say it has prime factors. So I mean, technically, I should sort of rule out x is equal to -3 separately. But if I just sort of plug in -3 here, I guess sort of -2 is a square, so that's not possible. And so actually, you can sort of rule out basically all negative numbers just by the fact that, like, except for -1, this left-hand side will be a negative number, so it will never be a square. Good. Okay, but so since x is, I can rule out negative numbers. Otherwise, I can just take x to be positive, and then x plus 2 is definitely at least 2, so it has a prime factor. And while they're all odd, so they're all odd just because x, so I'm assuming x is odd. I already ruled out the case where x is even. And they can't all be 1 mod 4, because then x would be. Sorry, then x plus 2 would be. And if I multiply together a bunch of prime numbers that are 1 mod 4, the result is still 1 mod 4. Okay, so I really deduced that since x plus 2 is congruent to 3 mod 4, I actually sort of do a little better. I can actually get a prime factor. So prime that divides x plus 2 that's congruent to 3 mod 4. Okay, so now I'm going to use this. And this right now, this seems like ridiculous. Like, what am I doing? But sort of there's some trick that lets me get some mileage out of this. And it sort of involves rewriting this equation. So if I look at sort of this equation, x cubed plus 7 is equal to y squared. Well, that's the same as saying x cubed plus 8 is equal to y squared plus 1. But now I can factor x cubed plus 8. I can factor that as x plus 2 times x squared minus 2x plus 4. Okay, and I'm saying that's equal to y squared plus 1. But since this prime q divides x plus 2, so it divides this, so it divides this left-hand side, so it also divides y squared plus 1. So y squared plus 1 is congruent to 0 mod q, i.e. y squared is congruent to -1 mod q. So -1 has a square root. Mod q. So this mod is prime q. There's something that squares to it, mod q, i.e., I mean, another way to say it is -1 is a square in the field with q elements. So remember, we're sort of working mod q is basically the same as working in the field with q elements. So right now, I mean, we just believe, based on this computation we did in the first couple of weeks of class, we believe this can't happen. Because q is congruent to 3 mod 4. And sort of, we notice this pattern where it seems like the only time that you can have a square root in the field with sort of q elements, where q is a prime, is if q is congruent to 1 mod 4. This is supposed to be an exclamation point. We don't think this can happen. So we'll verify this in a few weeks. And so that finishes the proof that there are no solutions. Okay, so sort of once we sort of see that fact is really true, not just sort of an observation that seems like it's true, we'll have finished this proof that there are no solutions to y squared is equal to x cubed plus 7. In other words, there's no squares that are 7 more than a cube. Okay, and so yes, it was some work, but like in the end, like we actually didn't do anything too complicated. Like we just used congruences, some factorization. We had to be a little bit clever, but we didn't have to do anything complicated. This is sort of really beautiful, like sort of congruences give you some tool you can use to analyze like integer solutions of equations. This is one of the reasons that they're useful. Okay, I'm going to stop there, and I will see you in class on Tuesday.